Okay, I won't be able to solve this equation today because it's going to be too long, but let me try to use this as a springboard to discuss what Frobenius solution is. So this happens to be a very well-known differential equation. It's I think it's called the Bessel's, but I'm not sure. But the solution is well known. It's sine x over x and cosine x over x. And it's like C1 of this plus C2 of that. That's the general solution. Now, does this have a power series? Well, the top one does have a power series, right?
Bottom one doesn't.
So let's see. Cosine x is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 6 factorial x to the 6th, so on and so on, right? What do you get if you divide by x then? Then 1 over x is what you get, and x squared divided by x. X to the 4th divided by x is x to the 3rd. Is this the power series? It's not because of this 1 over x. Okay? Power series are a series that starts from x to the 0th power to infinity. It doesn't include this. However, this one is a power series. If you can write it down. Sine x happens to start with x. So it's x minus 1/3 x to the cubed and all that. If you divide by x, it does give you a power series. So this differential equation actually has a solution that's like a power series, and another one which is not a power series. Now, we already know that x equal to 0 is not an ordinary point. How do you know that? If you divide by x, what do you get? You get y double prime plus 2 over x y prime plus y equal to 0. And what goes wrong at x equal to 0? 2 over x is undefined, right? When x is 0, 2 over x is undefined. So x equal to 0 is a singular point of this differential equation. And that's why you can't express all the solutions as power series around x equal to 0. Okay? But this mathematician named Frobenius was the first person to notice that even if you don't have a power series solution, there are some nice cases where you can write down the solution in the form of some modified power series. It's very close to a power series. And he investigated differential equations which were singular at 0 but still kind of allowing for these type of solutions. And now that method of solving and those type of singular points, it's all known. The method of solution is called the Frobenius solution. And his idea was to do the following. Rather than saying y is equal to sigma an x to the n equals to 0 to infinity, he included this x to the r. Well, if r is 0, then it's just a regular power series. So this contains the regular, usual power series method. But it's more general than just power series because, for example, if you set r equal to -1, x to the -1 is 1 over x, right? So you can express series like this one by putting it into this one. So this allows for more expressive expressions. So it can express things like that along with the regular power series. Okay? So that was his idea. Okay? And the reason this makes sense is if you have, so here's some examples. So apart from this, let's think about a purely hypothetical situation. If you had the power series like square root of x times something like a0 plus a1x plus a2x squared, whatever. Now, is this differentiable at x equal to 0? Is this function differentiable at x equal to 0? The answer is
Yes.
well, if you differentiate, it's 1 over 2 radical x times whatever. But you have to use the product rule, so radical x times this differentiate to 0, a1, 2a2x. That's what you get, right? Now try plugging in 0 to this. What goes wrong?
2 radical x.
1 over 2 radical x. If you try to plug in 0 here, you get 1 over 0. So if a0 is non-zero, then this would definitely cause a problem. If a0 is 0, then somehow you can cancel the square root of x and still you can manage. But then you will see that at some point the derivatives will not work. So he realized that some of these type of singular case would also yield solutions that look like this with some x to some rational powers, and it's something that's not expressible as a usual power series. If anything is expressed in power series like this, what kind of property does this function have? It has the property that no matter how many times you differentiate, you can still differentiate and plug in 0. This is differentiable infinitely many times at 0. You call such a function as a smooth function. And because this is not differentiable at 0, we know right away that if you have such a function, there's no way you can rewrite this in this form. So these are totally different kinds. They're very different. But having your solution to put into this form with r allowed to be like 1/2 or maybe -1, if you allow r to be some crazy numbers, then that takes care of a lot of these other special, really strange cases, and it expands the expressibility of the solution so that it can take care of equations like this. So that's where this idea of Frobenius comes in. Okay. So next time, I'm actually going to try to solve this using this form, and I'll show you how you can make sense out of these solutions.